Okay, so just want to say a few words about what Elasticsearch is. It's just a distributed RESTful interface on top of Lucene. Can you hear me? Can you hear me in the back? Oh. No?
Hardly.
I cannot speak well, no.
Okay. Come closer! Try shouting.
Lucene is an information retrieval library that's based on the inverted index and the Boolean model. I'll describe that later. No. So, in order to illustrate how inverted indices work, I create this very, very simple bunch of book with a bunch of pages, let's say, and then inverting this content into this form. So, just by looking at it, you can see that. So, for example, we get Perl benchmark, Perl Python benchmark, etc. Then we invert it. We have benchmark exists on, let's say, those documents, those pages. Perl exists on those pages, Perl on those pages, etc. So you can see that just by looking at that form, you can get a bunch of statistics for free. Like just looking at this hash, you know immediately how many documents have Perl, how many documents have, how many words we have in the whole book, how many documents have each word, etc. And so just remember for now that the documents are sorted by document ID. I'll explain that later. So if you want to run a query that is Perl and Ruby, you can see, just looking at that, for Perl and Ruby, you can see that just by intersecting the sets, you can immediately get the documents that match both terms. And in our case, if we can also do a OR kind of queries, so we can do Perl or Ruby, and looking at that again, we can just see, just by walking through the sets, you can immediately see all the documents that match your query. So it's really simple concept. And Lucene is pretty much just the best open source library that implements that. It's really actively developed. It is open source. It's extremely fast and really crackable. So, you know, in main libraries you cannot go against them. Like they pretty much put you in rails, and that's where you have to go. But with Lucene, that's not the case. You can pretty much do whatever you want. And Elasticsearch is now distributed. So everything there is a Lucene index, but even when you have the indices, you have to take care of things like, well, where do they go, how do you copy data, etc. Elasticsearch takes care of all that. It's an API and a whole bunch of cool plugins. It really works out of the box. So, for the purposes of populating that use case, let's say we have 100 million documents, and we have 200 words per document. That's a page. And then we have 1,000 searches per second. You can see zero tolerance for failure, let's say 10 milliseconds timeout. And it's a very important criteria. We have each query matches roughly 1 million documents. So each query has to do at least 1 million things to return results at minimum. So, in order to illustrate how much time it takes to do 1 million things, just all this really simple. Don't look at the code. It's just a simple. It's just a simple program that counts the even numbers from 0 to 1 million, and just does that. It takes 5 milliseconds on my laptop to do that. So doing almost nothing 1 million times actually takes 5 milliseconds. But if you look at the criteria that we had had 1,000 searches per second, which means that we have 1 millisecond to execute the search. So when you know that doing nothing 1 million times takes 5 milliseconds, then you actually have a problem. You cannot do that with one thread, with one unit of work. So I said that if I split that in pieces, then the numbers become a little bit better, and it seems that we'll be able to do that in 1 millisecond. So, splitting the 100 million documents into 120 shards. one thread has to work on average, only has to score on average only almost 9,000 documents, which is really a reasonable chunk of work we have to do. And I just, for simplicity, used 24 core boxes because that's like usually that we have a good thing. And with 5 boxes, we can actually do the work in reasonable amount of time. So that's what I did. I put literally 1/20th of 100 million documents in an index, and I made every 10th document to contain Perl and Ruby, and everything else contains only Perl. So all the documents in the index, they match on Perl, and every 10th they match has Ruby as well. And I just did a Perl and Ruby kind of query. So this thing took, again, 5 milliseconds on my laptop. When every other, so when we have a match every 10th document. But when all the documents are in a block, so basically we have the first 9,000 contain Perl and Ruby, then it only takes 0.7 milliseconds. Which, by the way, is almost as fast as this. It's only 14 times slower than this, just counting from the even number from 0 to 9,000. So why is that? That's like the difference. That's like 5 times, almost 10 times difference between having the documents in a block and having them every 10 documents. And let's say this is the case. We have 1 million documents that have Perl and 51,000 documents that have Ruby. And this is the same sorted list of document IDs that have those terms. So what happens is, when we say we want Perl and Ruby, there is no way we can have more results than 51,000. Just cannot happen. So we pick a leading query which is a smaller set. And then we say, okay, well, the leading is Ruby. Then we say, okay, the first document in Ruby is 300. Then we say, okay, well, advance this list to 300. Of course, we don't have 300 here. So we say, okay, my closest to 300 is 46,000. And so what we need to do is say, okay, well, advance Ruby to 46,000, but it doesn't have that one, it has 50,000. It is kind of jumps that makes a difference between having matches every nth document or every document, etc. So actually, and then pretty much repeat until the end. So this is how that's implemented in Lucene. It's literally the same as the same implementation that we just described. Just to show you that there's no like magic behind it. They cannot go to there. That's why they have to do infinite loops. But the important thing is that the position of the matches matter, and you cannot like ignore it. So why does like all this matter? The important thing is that it is linear with the number of matching documents. If you notice that I didn't talk about how many documents we have is completely irrelevant. Only matters how many documents match our query. Okay, so the total number of documents is irrelevant. Knowing that, you can plan capacity, and if you know your data, you can have estimation of worst cases. You can always predict this.
I have a question.
Yep.
You say the total number of documents is irrelevant, but if so, how do you do your ranking with your algorithms that use the number of documents versus...
No, but that's a constant. To take the number of documents that have a term, it's a constant lookup. That answer your question?
Yeah.
And you can, of course, knowing that, you can plan for stress because you can estimate your worst cases. So, to illustrate again like what's happening, we have 100 million documents, 100,000, no, 100 million documents. We are sorting them by relevance. The sort is usually TF-IDF, or it takes into account how many documents have a term, how many words does the document that matches on Perl has, and etc. Usually, of course, since it was BM25, I think BM21, you can do those. But they pretty much use different statistics because the relative index by itself gives you so much information. You have average number of items, average number of words in a document. You have all those things, so you can estimate how good a match is within a document based on the statistics on the document. We do that on the fly, and the whole thing happens within a few milliseconds. Into representing only 5 boxes. So, using Elasticsearch for that, we don't need to worry about this sharpness because you saw that we cannot do that with one thread. It just cannot happen. And somebody has to take care of that. We're talking about 120 pieces. They have to go around. We have to worry about replication and how we copy the data if we weren't using Elasticsearch. So Elasticsearch takes care of all that. So there's no magic involved. It's pretty much 120 shards and just scatter. Nothing, nothing magical. So the application will ask a box, and this box will ask a box, or you make a request to each of the shards that you need to query. And we do that for all of 120 shards, be it on 120 boxes, or 5 boxes, or 1 box, doesn't matter. It will ask all of them. And you just merge the results. You can merge easily because the score is usually comparable, so you can pretty much really discard results that you know that don't fit the limit. So far so good, but you have to take care of things like at the moment the use case that we invented, we have 5 boxes and 120 shards, and every request takes all the resources from the system. Like there's nothing can go wrong. No boxes go down, and this doesn't happen. So things will die, and so we have to take care of that. We cannot have downtime. We cannot do maintenance, and we have to figure out how to do monitoring properly. And we also have to take care of GC, which is a major problem. It will happen, and to stop the world of GCs can stop your application for like, let's say, a second, depending on the heap size. So, pretty much the solution to all those problems is add more boxes. If you increase the number of replicas, which means that one shard can live on more than one box. You ought to put in resilience, so more boxes can be done at the same time. Just increasing the number of shards decreases latency because the unit of computing gets more. Of course, at some point, the overhead of communication overhead will become a problem. And so what you do to upgrade, when you had to upgrade the Elasticsearch of Java or the kernel of the boxes, so what you can do is you can do just a rolling restart, which means just you take the box out of the cluster, you update it, whatever you have to do, and put it back in. You can of course do a cluster restart, which basically bring everything down, update, and hope. And you can do a cluster split, which is so let's say you split the cluster in half if you can afford that capacity-wise. And then you update half the cluster, and then you just run boxes one by one in the other cluster, or you can just do only 2 updates. You update one half and then the other half. And you can do the growing cluster, which is take one box out and then start moving updated boxes to it in a new cluster. During all those operations, you have to be, like also during the whole cluster's lifetime, you have to consider that the masters are a little bit fragile, and they do very little things, but they're very important. And if they fail to do them, bad things happen. And so they care of things like addition and removal of nodes, creating, like moving indices around, shard relocation. So they decide where the primary shards are. And when a box goes down that holds the primary shard, they will promote a replica to be the primary shard, and they will update the cluster state that that's the using state. And so you can imagine that when things go crazy, like have a few boxes going down, and these shard revocations start to happen, and you want your masters to not be busy doing something else. So the worst thing that can happen is this kind of split brain, which means that, so let's say we're in this state, everything's okay, and then all of a sudden, I don't think you can see that, but there's a line right in the middle of C. So A sees C, doesn't see B, and B also sees C, and B is left in a masterless cluster because he doesn't see the master. So it will hold an election, it will win. And then what happens after that is, well, you have two masters. And then imagine this guy had a replica promotes it to primary shard, and you did an insert, and then all of a sudden you have a data vault because the new document is defined here, and the shard will never be able to be merged. You cannot merge that because you have different. This one also thinks he has a primary shard, let's say shard 7, and this one promoted his replica into a primary. So when you did the insert, you cannot go back. You either have to delete it from here or let it hold. To avoid that, you can set the minimum number of master eligible nodes to number of boxes divided by 2 plus 1. So in that case, if that happens, this will say, okay, well, in that case, that's 2. So even in the Elasticsearch before 1.3, this was still an issue because you can see that with 3 boxes, you have to set it. When you set it to 2, that's still the case because this is eligible and this is eligible, and that's still 2 boxes that can be mastered. So this will still win the election. And it was just a situation where you lose data. But they fixed that in 1.4, I think. So it's safe now. Not sure how they fixed it. Or you can use the zookeeper plugin, which also avoids this situation.
How does B know? If B can't see A, then how would B know that there were any masters and that it could not become master itself? If it can't see the master, it must think, hey, there's no masters.
That's what I mean. If you hold an election, it will win.
Yeah, but so how does that solve the problem? But if you limit masters,
that's exactly. Even if you set that, you still have the issue with the same. B can still win.
so the Elasticsearch update fixed it somewhere else.
Yeah, well, I'm not sure how they fixed it. We stopped using Elasticsearch before.
So, question? Maybe they used a consensus algorithm, Paxos, or?
Well, what they use, I think it was inspired by Paxos. They have always been using the consensus algorithm, and I think it was inspired by Paxos. But this is more of a so I'm not really sure how they. I'm not sure how they fixed it. It was really recent fix, and I can't answer. But it was really a problem. And pretty much the way you can avoid it is by setting this number to a big number. Let's say you can set it to 3, right? If you set it to 3, then you have no issue because when that split happens, it will not do anything. But the problem is when that split happens, this will also stop working because they don't have enough eligible masters. So it's having a dedicated master node really reduces the chances. Alright, how do you do monitoring? So you have to be really careful about the number of indexing threads, searching threads. You have to grab those. You have to watch your heap. You don't want to use more of the heap than you actually need because the bigger the heap is, the more GCU, stop the work GCU time you have. So be careful with that. And you have to keep in mind that watching from outside is not enough because every box talks with every box. So if you're outside of the whole system and then you just see my monitoring daemon sees everything okay, that's not enough. And it means you have to watch from every node how you see the whole cluster and then look at that. You have to watch across all 1,000 filters. Every write, when you write a document, you create a new scene segment. This is like 10,000 filters. At some point there will be more index, but it's still when you have many writes and many shards, this can become important. And of course, if you can start with JMX, which is a Java thing, you do like profiling and thread them and keep them. do outside debugging, it's really helpful. So what I've seen so far with a couple of the last years, I guess, we've seen like random stopping services using 100% CPU, don't know why. Reboot the box, never start again. Random crashes, panics, like all kinds of dead logs. Broken TCP states, like the last service boasting that the connection is open, but the other boasting is not. Switches sending traffic only to odd MAC addresses.
Odd like in weird or
No, odd.
not even.
Yes, not even.
Okay.
Sleep firmware methods. And this was a really cool one. Like everything that was started before a certain point works, and after a certain point becomes a zombie kind of thing. Almost all of those were like hardware issues that manifest themselves in really, really weird ways. And everything is untestable, of course, and unreproducible. But my point is, so you have these kinds of issues happening, and then you have a distributed system that has to make decisions for you, usually under heavy pressure, and that's kind of shaky. So what actually, how we started, we actually just wanted to store stuff and search it. We didn't want anything, any of those crazy things. So I want to show you how you can store a JSON input directly into C, like a key value input, and then store directly into C. And you can see it like 20 lines of code, and that's with the Java. And it's not magic. It's really, really straightforward, and the documentation is amazing, and they're really helpful guys. This is the same about how you search in C. This is we created two Perl queries. Perl and Ruby, and they say they must occur together, and then say do the search and get the result. That's it. There's no 20 lines. It's pretty much, if you do that in Perl, it will be the same lines. So it's really easy to hack your own search. You can use like some HTTP or native or JT or MarkTTY to get the top end, because you have to keep in mind that the scores are comparable. So it's really easy to merge results. It's really, really easy. And you can just copy using files around. So you get the top end pretty much result by score and then put them together. And of course, you have your own problems. And a short summary is like nothing is as easy as it seems. Like there's no silver bullet. Bad things will happen, and everything can improve, right? So it's better if your swing is broken, and like just plan for it. And really don't be afraid to just hack your own things. It's not. Nobody's doing magic anyway. Just straightforward things. And the inverted index implementations are really, you saw that the inverted index is really simple and straightforward. So don't be afraid of that. Oh, and one more thing is that usually when it comes to distributed systems, you know when the range improves kinda, so it starts thrashing, it goes down really fast. It's kind of hard to repair. Especially in a write heavy system, it's really hard to recover. This is a bunch of, you can see that